When the universe began, it made matter and antimatter in perfectly equal amounts. They should have wiped each other out in the first second, leaving nothing behind. No stars, no planets, no you. But something broke the rule. One particle in every billion survived, and every galaxy you see is built from those survivors. Now, deep beneath the French and Swiss border, scientists at CERN may have caught the rule breaking in real time. A signal in baryons, a whisper in neutrinos, a crack in the symmetry that built reality. If you want to understand why anything exists at all, stay with me. Like and subscribe. We begin. Every atom in your body is the result of a mistake. A mistake the universe was never supposed to make. According to the laws of physics as we understand them, the Big Bang should have produced exactly equal amounts of two things. Matter, the stuff you and everything around you is made of, and antimatter, its mirror twin. Same mass, same behavior. Opposite charge. When the two meet, they destroy each other completely, converting their entire mass into pure energy in a flash of light. So when the universe was born, almost 14 billion years ago, the math is simple and brutal. Equal matter, equal antimatter. They should have collided in the first fractions of a second, annihilated each other entirely, and left behind nothing but an empty cosmos filled with cooling radiation. No galaxies, no stars, no planets, no chemistry, no life, no one to wonder about any of it. And yet, here you are. Reading these words, made of atoms that should have vanished long before the first second of cosmic history was complete. This is the problem physicists have stared at for more than 70 years. It has a name. The matter-antimatter asymmetry problem. Or sometimes the baryon asymmetry of the universe. Strip away the technical words and the question is simple. Why is there something instead of nothing? The numbers behind it are almost absurd. For every billion particles of antimatter the early universe produced, it produced 1 billion and 1 particles of matter. That single extra particle, repeated trillions upon trillions of times, is the entire reason anything exists. Every star you see in the night sky, every grain of sand, every breath you take, all of it, leftover scraps, survivors of an annihilation event so total it should have left the cosmos sterile. For a long time, scientists assumed there had to be a clean explanation. Maybe the antimatter was just hiding. Maybe it had been pushed to a distant corner of the universe, sitting in galaxies we had not yet seen. Maybe the imbalance was an illusion of incomplete observation. That hope did not survive. Decades of careful searching have shown that the universe is, as far as we can detect, made overwhelmingly of one kind of stuff. Matter. The antimatter is gone. Erased. Or, more precisely, it was never quite there in the same quantity to begin with. Which means the problem is real. And it is enormous. Something in the very first instance after the Big Bang tilted the scales. Some unknown process gave matter the slimmest possible advantage over its mirror twin. That advantage was so tiny it would barely register on any human measurement. But it was just enough. Enough to leave behind the residue we now call the visible universe. Here is what makes it haunting. The standard model of particle physics, the most accurate theory ever built, predicts the imbalance should have been even smaller than what we observe, by a factor of about 10 billion. That gap between prediction and reality is one of the largest unsolved problems in physics. And it is exactly the gap that scientists at one specific place on Earth have spent decades trying to close. A facility built to recreate the conditions of that first moment. A machine designed to catch the universe in the act of breaking its own rules. What they found in 2025 changed the search forever. When matter meets antimatter, the result is the most violent reaction in physics. Not an explosion in the ordinary sense, not heat, not fire, something cleaner and far more total. When a particle touches its antiparticle, both vanish completely. Their entire mass converts into energy, released as high-frequency light called gamma radiation. No residue, no fragments, no leftover dust. The interaction is 100% efficient. Nothing else in nature comes close. To put that in human terms, a single gram of antimatter meeting a single gram of matter would release energy comparable to a large nuclear weapon. 2 grams of stuff, reduced to pure light. That is the rule the universe lives by when these two forms of substance touch. Now picture the early cosmos, a region smaller than a proton, hotter than anything that will ever exist again. Energy pouring into existence and condensing into pairs of particles. Every time a particle of matter appeared, an equal antiparticle appeared with it. They formed and annihilated and reformed, locked in a furious cycle that should have stayed perfectly balanced. As the universe expanded, it cooled. The energy density dropped. New particle pairs stopped forming. What remained was supposed to finish the job. Every electron meeting a positron. Every quark meeting an antiquark. Every proton meeting an antiproton. A wave of mutual destruction sweeping across the cooling cosmos until only photons were left behind. That ending nearly happened. The annihilation was almost complete. Today, when astronomers measure the cosmic microwave background, the faint glow left over from the early universe, they see exactly what the aftermath of that destruction should look like. A vast sea of photons, around 400 per cubic centimeter of space, in every direction. These photons are the ashes of the Great Annihilation, the light from particles that did find their partners and were erased. For every one of us still here, there are roughly 1 billion of those leftover photons. That ratio is not an estimate. It is one of the most precisely measured quantities in cosmology. 1 particle of matter survived for every billion that died. The horror of that number is hard to grasp at first. The early universe was nearly empty by the time the dust settled. What we now call the visible cosmos, all the galaxies and gas and stars stretching for tens of billions of light years, is the thin remainder of a much larger original population. The night sky is a graveyard with a few survivors flickering in it. Here is the part that should not work. If the books had balanced perfectly, there would be no survivors at all. The annihilation would have been clean. Total. Final. The universe would be a featureless ocean of cooling light, and no atom anywhere would have ever formed. No hydrogen, no carbon, no oxygen. The chemistry that makes you possible requires baryons, and baryons require that someone, somewhere, broke the rule of equal pairing. Something must have stepped in during those first slivers of time and changed the rules. Something gave matter a tiny edge, so small it almost vanishes when you write it down. So decisive that without it, you would not be here. That something is what physicists call a violation, a break in a symmetry the universe was supposed to obey perfectly. And to find it, they had to start by understanding what every particle has waiting for it on the other side of the mirror. Every particle in your body has a twin somewhere it will never meet. When physicists first wrote down the equations describing how matter behaves, they noticed something strange. The equations had 2 solutions. One described particles as we know them, the other described particles with the opposite electric charge but identical mass. At first, this seemed like a mathematical curiosity, a trick of the math that surely had no real meaning. Then, in 1932, a young physicist named Carl Anderson was studying cosmic rays in a cloud chamber, a device that lets you see the tracks of charged particles moving through gas. He noticed a track that curved the wrong way. It looked exactly like an electron, with the same mass and the same behavior, but its path bent in the opposite direction inside a magnetic field. That meant it had positive charge, where an electron has negative charge. He had found the anti-electron, or as it is now called, the positron. the mirror twin of the lightest charged particle in nature. The math had been right. The universe really did come with a hidden second copy of itself, made of opposite charge versions of every particle we know. Within decades, every particle physicists discovered came with its own antiparticle. The proton has the antiproton. The neutron has the antineutron. The neutrino has the antineutrino. Quarks, the building blocks inside protons and neutrons, all have antiquarks. The pattern is total. There is no known particle in the standard model that lacks an antimatter twin. The two sides of the mirror are nearly identical. They have the same mass to extraordinary precision. They obey the same laws of motion. They feel gravity the same way. They participate in the same nuclear forces. If you somehow built a person entirely out of antimatter, antiprotons in the nuclei, and positrons in the orbits, that person would look, move, and think exactly like a normal person. From the inside, they would have no way of telling the difference. The only way you would know is if the two of you ever shook hands. The instant your skin touched theirs, both of you would convert into a flash of light bright enough to outshine cities. That is the strange beauty of the antimatter twin. So similar that the laws of physics treat them as essentially the same. So opposite that contact between them is total destruction. The problem this creates for cosmology is now sharper. If every particle has a twin, and the twins behave the same way, then the early universe had no reason to favor one over the other. Energy turning into matter should turn into matter and antimatter at equal rates. The two populations should have been mathematically identical at every instant, yet they were not. Somewhere in the rules describing how these particles interact, there is a tiny difference, a subtle preference. A bias that gives matter the edge. The standard model knows this difference exists, because experiments have measured it for over 60 years. What the standard model cannot do is explain why the difference is large enough to leave behind a universe. Finding the source of that bias means looking very closely at the moments when particles transform into other particles, because that is where the symmetry, when it does break, leaves its fingerprints behind. And the size of the surviving fingerprint tells a stranger story than anyone expected. One particle in every billion is the reason you exist. That is the actual number. It comes from comparing two things astronomers can measure with high confidence: the amount of ordinary matter in the universe, calculated from how galaxies move and how the cosmic background radiation is patterned, and the number of leftover photons, the ancient light from the early annihilation. Divide one by the other, and you get a ratio. Roughly 1 part in 1 billion. That is how much matter outweighed antimatter in the first moments after the Big Bang. Hold that scale in your mind for a moment. Imagine a stadium packed with 1 billion particles of antimatter on one side and 1 billion particles of matter plus one extra on the other. Now imagine the two crowds rushing into each other. Every pairing destroys both. The light produced is almost too bright to comprehend. When the dust settles, only that single extra particle is left standing. Alone, surrounded by radiation. The lone survivor of a battlefield with 2 billion casualties. That single particle is the seed of everything you have ever seen. Multiply the scenario by every cubic meter of space across the observable universe. Multiply it again by every second of those first few moments after the Big Bang. The numbers become incomprehensible quickly. But the ratio stays the same. 1 survivor for every billion pairs. That is the thin margin by which the cosmos exists. Here is what makes the number even more unsettling. It cannot be a coincidence. If the imbalance had been smaller, by even a factor of 10, the universe would have ended up too empty for galaxies to form. The leftover matter would have been spread too thinly for gravity to pull it together. No stars would have ignited, no heavy elements would have been forged. The cosmos would be a cold, sparse fog of hydrogen with nothing happening in it. If the imbalance had been larger, the opposite problem would have struck. Too much matter condensing too quickly, collapsing into black holes before stars could form. The structures that fill the night sky depend on this exact ratio being almost exactly what it is. The universe sits inside a narrow window of possibility, and that window was set in the first second of its life. Cosmologists have a precise label for this number. They call it the baryon to photon ratio. It is one of the small handful of fundamental numbers that determine the entire history of the universe. Change it slightly, and the cosmic story unravels. Change it more, and there is no story at all. Now consider what this means for the search itself. Whatever broke the symmetry between matter and antimatter did not produce a small effect that grew over time. It produced one specific number, fine-tuned to within tight bounds, and locked in within the first fraction of a second after the universe began. The mechanism worked once, it worked everywhere, and it left almost no trace, because nearly all of its evidence annihilated itself. What we are left with is the residue, a faint echo of an event no one was around to witness. To find the cause, scientists cannot rebuild the early universe directly. But they can do the next best thing. They can look at how particles behave today in carefully controlled collisions and search for any sign that the same bias still operates. And the rule those particles were supposed to obey, the rule that made the symmetry feel so unbreakable in the first place, hides one of the deepest assumptions in physics. For most of the 20th century, physicists believed the universe came with a guarantee. That guarantee had a formal name. It was called CP symmetry. The letters stand for two operations: C for charge, the act of swapping a particle for its antiparticle; P for parity, the act of flipping space like a mirror image. Apply both at the same time, the theory said, and the laws of physics should look exactly the same. A universe of antimatter viewed in a mirror should behave identically to our own universe of matter. There would be no way to tell them apart from physics alone. This idea was deeply attractive. It meant the cosmos played fair. The two sides of the mirror were not just similar, they were perfectly equal under the right transformation. There was no preferred direction, no preferred kind of stuff, no reason for the universe to favor one twin over the other. The belief in CP symmetry was so strong that when experiments hinted otherwise, physicists were genuinely shaken. Because if the symmetry was real, then matter and antimatter were partners in every possible sense. And if they were true partners, then the early universe had no reason to choose between them. The problem is now obvious. We exist. The choice was made. Either CP symmetry is broken at some level, or there is some other process beyond it that tilted the early universe toward matter. There are no other options. The math forbids every alternative. Without some violation somewhere, the books balance, the annihilation is total, and nothing remains. So the search began. Not for the reason matter exists. Not yet. First, for any sign at all that this fundamental symmetry could be broken. Even slightly. Even rarely. Even in some obscure corner of particle physics that seemed irrelevant to everyday matter. Because once you find a single crack, you have proof the universe is capable of choosing sides. And once you have that proof, you can start asking how big the crack really is, and whether it is wide enough to explain a cosmos. The first major test came from a strange family of particles called kaons. They were unstable. They decayed quickly into other particles, and they came in two forms, one made of matter and one of antimatter, that ought to behave identically if CP symmetry held. If the rule was real, you could swap one for the other and see the same patterns of decay in the same proportions every time. That assumption was about to fail. What followed shocked the physics community in 1964 and set off a 60-year hunt that continues right now. The cracks turned out to be real. Small, subtle, rare enough that you needed careful experiments to see them at all. But they were there. The universe, it turned out, did keep books with a slight tilt. The mirror was not perfectly clean, the implications spread quickly. If CP symmetry could break in one corner of physics, it might break in others. Each new violation, no matter how small, was a possible clue to the original imbalance. Each one was a piece of the puzzle that had to add up, eventually, to one extra particle in every billion. But the first crack appeared in the smallest and most unexpected place, and the way it was discovered set the tone for everything that came after. In 1964, a single experiment in New York changed the meaning of the universe. Two physicists, James Cronin and Val Fitch, were working at Brookhaven National Laboratory on Long Island. They were studying kaons, those short-lived particles that come in matter and antimatter versions. The accepted view was clear. Kaons should decay in patterns that respected CP symmetry perfectly. If a particle of one kind decayed into a certain set of products, its antimatter twin should decay into the corresponding mirror products at exactly the same rate. No deviation. No surprises. The team set up a careful experiment to test this assumption. They expected to confirm what every theorist already believed. Instead, they found a tiny anomaly that should not have been there. A small fraction of kaons were decaying in a way that violated CP symmetry directly. Not a lot. About one decay in every 500. A whisper of an effect, barely above the noise, but unmistakable once they checked it. The result landed like a quiet earthquake. Physicists had assumed CP symmetry was as fundamental as the speed of light. The discovery showed it was not. The mirror had a flaw. A small one, but a real one. Cronin and Fitch later won the Nobel Prize for the work, but the scientific significance went far beyond the award. For the first time, there was experimental proof that the universe could distinguish, in some subtle way, between matter and antimatter. The two were not perfectly equal. They obeyed the same rules to high precision, but not to perfect precision. A slight asymmetry was baked into reality itself. This was enormous. It meant the mechanism that produced the cosmos out of nearly equal twins might have a foothold in known physics. If CP could break in kaon decays, it might break elsewhere too. And if it broke in enough places, with enough strength, perhaps the imbalance of matter and antimatter could finally be explained without invoking anything exotic. The hope, however, ran into a wall. As physicists carefully measured the size of the kaon effect and looked for similar effects in other particles, they kept finding the same thing. The violations were real, and they were now understood within the standard model of particle physics. But they were tiny. So small that when you fed them into the equations describing the early universe, the predicted leftover matter came out to roughly 1 part in 10 billion billion, not 1 part in 1 billion. The math fell short by a factor of about 10 billion. That gap is not a rounding error. It is the difference between a universe full of galaxies and a universe with almost nothing in it. The known violations of CP symmetry, even taken together, are nowhere near strong enough to explain why we are here, which means the 1964 discovery was both a triumph and a warning. The crack was real, but it was too narrow. Something else, something larger, must be operating in the laws of nature. Some additional source of asymmetry that the standard model has not yet captured. A hidden mechanism sitting somewhere in the structure of physics, waiting to be found. To find it, scientists needed bigger machines, more sensitive detectors, and access to particles the early universe had touched directly. The kaon was only the beginning. The hunt was about to move underground, into a tunnel beneath the border between two countries, where the largest scientific instrument ever built was being prepared to take up the chase. A few hundred feet underground, on the border between France and Switzerland, sits the largest machine humanity has ever constructed. It is a ring. 17 miles around, buried deep enough to be shielded from cosmic rays and stable temperature shifts. Inside, 2 beams of protons race in opposite directions at nearly the speed of light, guided by powerful superconducting magnets cooled to colder than outer space. When the beams cross, the protons smash into each other with enough energy to briefly recreate the conditions that existed less than a trillionth of a second after the Big Bang. This is the Large Hadron Collider. The flagship instrument of the European Organization for Nuclear Research, known by its French acronym CERN. And while it is famous for many things, including the discovery of the Higgs boson in 2012, its quieter and arguably more important mission has always been to investigate the deepest mystery in physics. Why does matter exist? The reason CERN became the courtroom for this question is straightforward. To study how matter and antimatter behave differently, you need to produce both in enormous quantities, under controlled conditions, with detectors precise enough to measure differences smaller than 1 part in 1,000. Cosmic rays cannot do it. Nuclear reactors cannot do it. Only a machine that can collide particles at the energies of the early universe again and again, billions of times per second, can produce the data needed to catch the asymmetry in action. Inside the tunnel, the protons collide and shower the surrounding detectors with debris. Most of that debris consists of short-lived particles that exist for only a fraction of a second before breaking down into more stable products. Among those particles are exactly the ones physicists need. Mesons, baryons, particles built from quarks capable of existing in matter and antimatter versions, with decay patterns sensitive to even the tiniest CP violation. When a beam of these particles is produced, they decay before they can travel more than a few millimeters. The detectors must capture every fragment, reconstruct the full event from the trails left behind, and determine which type of particle started the whole cascade. Doing this once is hard. Doing it billions of times, with statistical precision, is one of the great technical achievements of modern science. CERN runs several such detectors along the LHC ring, each tuned for different goals. The general-purpose ones, Atlas and CMS, were the workhorses behind the Higgs discovery. But for the matter-antimatter question, a more specialized instrument was needed. A detector designed not for high-energy debris from head-on collisions, but for the careful tracking of particles that fly forward at slight angles, carrying with them the rare and delicate signals of CP violation. That detector has its own name, its own building, and its own dedicated team. It has been collecting data for over a decade, and in 2025, it produced a result that physicists had been chasing for more than half a century. A result that did not solve the problem, but pinned down where to look next. A result that showed, for the first time, that the asymmetry between matter and antimatter could be seen in the very particles that make up everything around us. Before that result could mean anything, however, the machine that found it had to do something no instrument before it could. It had to watch matter and antimatter behave differently in real time. The detector that did it is called LHCb. The letters stand for Large Hadron Collider Beauty, a reference to the beauty quark, also known as the bottom quark, one of the heaviest particles in the Standard Model and a frequent home for CP-violating effects. The detector sits in a cavern next to the main collider ring, about 350 feet underground, and it does not look like the giant cylindrical instruments that dominate other parts of CERN. LHCb is long, forked, asymmetric, built like a forward-facing telescope rather than a sphere. The reason for this odd shape is physics. When two protons collide head-on at high energies, the heavy beauty quarks produced in the smash tend to fly forward at sharp angles, close to the original direction of the beam. A spherical detector wastes its surface on regions where these particles do not go. LHCb is shaped to catch them where they actually appear, lining up its tracking layers, calorimeters, and magnetic spectrometers in a long row that extends downstream from the collision point. Inside, the precision is staggering. The detector can pinpoint the location where a particle was created and where it decayed, sometimes only a few millimeters apart, with accuracy down to about 1,000th of an inch. It can identify the type of each daughter particle by measuring its speed, charge, and energy. And it can do all of this at a rate of roughly 40 million collisions per second, sorting through the chaos in real time and saving only the rare events that matter for the search. That sorting is its own miracle of engineering. The vast majority of LHC collisions produce nothing interesting from a CP violation standpoint. Out of millions of events, only a small handful contain the specific particles physicists need. The detector's electronics make split-second decisions about which collisions to keep and which to discard, throwing away terabytes of data per second to focus on the rare jewels. Once collected, the events are reconstructed by software. Each surviving collision is replayed in 3 dimensions inside a computer. Tracks are matched, vertices are identified, particle identities are assigned. The team then compares the rates at which matter particles decay into certain products against the rates at which their antimatter counterparts decay into the mirror products. If the 2 rates are perfectly equal, CP symmetry holds for that particular decay. If they differ, the symmetry is broken. Over the past 15 years, LHCb has confirmed CP violation in many decays involving the beauty quark and its lighter cousin, the strange quark. Each measurement was a win, but each one also fit comfortably within the predictions of the standard model. The effects were real. They were just not large enough to explain the universe. For decades, one category of particle had stayed silent on the question. Baryons, the class that includes protons and neutrons. The class that makes up everything you can touch. CP violation had been seen in mesons, which are made of 1 quark and 1 antiquark. It had not been seen ever in baryons, which are made of 3 quarks bound together. Theory said it should exist there too. Experiments had not yet confirmed it. In 2025, LHCb finally cracked it open, and the particle that gave up the secret had a name straight out of physics tradition. The particle is called the lambda baryon. It is heavy, unstable, and rare. Built from 3 quarks, one of which is the beauty quark, it lives for roughly a trillionth of a second before decaying into lighter particles. In every collision at the LHC where a beauty quark is produced, there is a small chance the quark will end up bound inside a lambda b. And in every lambda b that forms, there is a smaller chance still that it will decay into a particular set of products that allow CP violation to be measured cleanly. For years, the LHCb team had been collecting these rare decays patiently, building up statistics, comparing the behavior of the matter version, the lambda b, against the behavior of its antimatter twin, the anti-lambda b. The 2 should decay at the same rate into mirror image products if CP symmetry held in baryons. For most of the past decade, the data was not quite sufficient to declare a difference with certainty. The signal was there in some hints, but it sat just below the strict statistical threshold physicists demand before announcing a discovery. In 2025, after running through a much larger data set collected during the LHC's most recent operating period, the team crossed that threshold. The matter and antimatter versions of the lambda b were decaying at measurably different rates. The asymmetry was small, only a few % in the relevant channel, but it was statistically solid. CP violation in baryons had been observed for the first time in history. The result was published, peer-reviewed, and widely covered in the physics community. To anyone outside that community, a few % difference in a rare decay might sound underwhelming. Inside the field, it was a landmark. Theory had predicted CP violation in baryons should exist. The standard model required it. But for 60 years, no experiment had been sensitive enough to confirm it. The 2025 measurement closed that gap. Why does this matter for the cosmic question? Because baryons are the particles that survived. The universe today is dominated by protons and neutrons, which are baryons. The asymmetry that left them behind, whatever caused it, had to act on baryons specifically. Watching CP violation appear in mesons was helpful but distant from the actual survivors. Watching it appear in baryons, in particles cousin to the building blocks of every atom, brings the laboratory measurement directly in line with the cosmic mystery. The discovery did something else. It confirmed that the Standard Model's predictions extend further than anyone had directly verified. The size of the violation in the lambda B decay matched what the theory said it should be. That match is a victory for the theory and, paradoxically, a reinforcement of the problem. Because if the Standard Model predictions hold all the way through baryons, then the same shortfall that has plagued cosmology remains. The known mechanism is too weak. The asymmetry it produces is too small, by a factor of about 10 billion, which means the 2025 result is best understood as a checkpoint. The map is now more accurate. The known sources of CP violation have been seen in both mesons and baryons. They behave as predicted. And they still cannot explain the cosmos. The hidden source of the imbalance must lie elsewhere, in particles or processes the LHC has not yet produced, or in physics that operates at energies far higher than any earthly machine can reach. To understand why this matters so personally, look down at your own hand. Every cell in your body is made of baryons. A proton in the nucleus of a hydrogen atom is a baryon. A neutron beside it is a baryon. The carbon, oxygen, nitrogen, and other heavier elements that build your tissues are constructed from atoms whose nuclei contain protons and neutrons in different counts. All baryons. The electrons that orbit those nuclei are not baryons, but they make up a tiny fraction of your mass. Strip them away, and you still have most of yourself. Strip away the baryons, and there is nothing of you left. A baryon is, by definition, a particle made of 3 quarks bound together by the strong nuclear force. Protons are the most common kind, with 2 up quarks and 1 down quark. Neutrons are nearly as common, with 1 up quark and 2 down quarks. Heavier baryons like the lambda B contain different combinations, often including one of the heavier quark types, and they are unstable, which is why they appear only briefly in collisions before decaying into lighter products. The reason this matters for the matter-antimatter problem is direct. The cosmic imbalance is, more precisely, a baryon imbalance. The universe today contains protons and neutrons, but almost no antiprotons or antineutrons. The number of leftover baryons per leftover photon, that ratio physicists track so carefully, is what cosmology actually measures. When scientists say matter 1, they mean baryonic matter 1. This connects the laboratory work to the cosmic story in the most concrete possible way. The lambda B result observed in 2025 is the first time anyone has watched CP symmetry break inside a baryon, the same family of particles that makes up your body. Whatever process tilted the early universe toward survival must have favored baryons specifically. Now there is direct experimental evidence that baryons can, in fact, behave differently from their antimatter twins. Without that property, no baryogenesis is possible. The word baryogenesis describes any mechanism that produces an excess of baryons over antibaryons in the early universe. Every theory of how matter came to dominate falls under that label. Every such theory requires CP violation in baryons as a necessary ingredient. Until 2025, that ingredient had been theoretical. Now it is observed. A subtle point sits underneath all of this. The CP violation seen in the lambda B is small, a few percent in the specific decay channel measured. That is far larger than the cosmic imbalance, which is 1 part in a billion. So the size is not the problem. The problem is that this kind of CP violation, embedded within the Standard Model, only operates at very high energies and only across certain combinations of quarks. When the math is run forward in time, projecting the effect onto the cooling early universe, it does not produce enough surviving baryons. The effect is real. The effect is too restricted. So the 2025 measurement does two things simultaneously. It shows that baryons themselves can break CP symmetry, and it confirms that the kind of breaking the standard model predicts, while now observed in the right family of particles, is still not enough. Three conditions, written down decades ago by a Russian physicist working in isolation, define exactly what any successful explanation must include. They are the rules of the game. Any theory of why you exist has to satisfy all three, and they are stricter than they sound. In 1967, a Soviet physicist named Andrei Sakharov wrote down a list. He was not famous for cosmology at the time. He was better known for designing nuclear weapons for the Soviet Union, work he would later renounce as he became a leading dissident and human rights advocate. But in a short paper that year, working through the logic of how matter could have survived the early universe, he laid out three conditions that any successful explanation must satisfy. The list became one of the most quoted in modern physics. It is now known simply as the Sakharov conditions. The first condition is that baryon number must not be conserved. Baryon number is a count of how many baryons a system contains, counting antibaryons as negative. If baryon number is perfectly conserved, then the universe must have always had whatever excess it has now. Since cosmology strongly suggests the early universe began with no net baryons, some process must have created an excess from nothing. That requires interactions that violate baryon number conservation, even if only rarely. The second condition is that CP symmetry must be broken, along with another related symmetry called C-symmetry. This is the rule the universe was supposed to obey perfectly, the one cracked open by the kaon discovery in 1964 and now confirmed in baryons in 2025. Without CP violation, even baryon number violating processes would produce equal numbers of baryons and antibaryons. The breaking of CP is what allows the production rates to differ. The third condition is that the universe must have been out of thermal equilibrium during the relevant period. Thermal equilibrium is a state of perfect balance, where every process is matched by its reverse at the same rate. In such a state, any baryons created are immediately destroyed at the same pace, and no net excess accumulates. Only when the universe is changing rapidly, expanding and cooling fast enough that reactions cannot keep up, can an imbalance get locked in before it dissolves. All three conditions must hold simultaneously. Drop any one, and the matter excess is impossible. Sakharov's insight was that these were not just useful guidelines, but mathematical requirements baked into any theory that aspired to explain the cosmos. The standard model satisfies all three conditions. Technically, baryon number can be violated by exotic processes called sphaleron interactions, which only operate at very high temperatures. CP can be violated as shown in mesons and now baryons, and the early universe was demonstrably out of equilibrium during its rapid cooling. All three boxes get checked. The trouble is in the magnitudes. The standard model satisfies the conditions but only weakly. The CP violation it predicts is far too small to produce the observed imbalance. The baryon number violating processes it allows operate at the wrong times in cosmic history. The departure from equilibrium it permits is not strong enough to lock in a sufficient excess. When all the pieces are put together, the predicted ratio of leftover matter to photons comes out about 10 billion times smaller than what we actually measure. That is not a small disagreement, it is a chasm. Some additional source of CP violation, or some additional baryon number violating process, or some stronger departure from equilibrium must have been operating in the early universe, and whatever it was, the standard model has not yet captured it. The shortfall has a name in the field. It is called, with admirable understatement, the baryogenesis problem. The standard model is the most successful scientific theory ever built. It describes every known particle and 3 of the 4 fundamental forces with stunning accuracy. Predictions made by the theory in the 1970s have been confirmed to 10 decimal places. The discovery of the Higgs boson in 2012 was the final missing piece in its predicted family of particles. Across decades of experimental tests at energies ranging from low-temperature atomic physics to the highest reaches of the LHC, the standard model has held up. So when the same theory fails to explain why matter exists, the failure carries weight. It is not the failure of a guess or a partial framework. It is the failure of the most thoroughly tested description of nature humanity has ever produced. Something is missing from the picture, and the size of what is missing must be substantial. Within the standard model, CP violation arises from a specific source. The mathematical structure that describes how quarks change from one type to another contains a single complex number called the CKM phase, named for the 3 physicists who developed the framework. This phase is the engine behind every CP violating effect the standard model predicts. Tune it to the value measured in experiments, and you can calculate exactly how much CP violation should appear in kaons, in B mesons, in the lambda baryon, and so on. The predictions all match observation. The same phase, when used to predict the cosmic baryon asymmetry, gives a number that is far too small. Calculations performed in the 1990s and refined many times since show that the CKM phase, even combined with the high-temperature sphaleron processes, can only produce a baryon to photon ratio of around 1 part in 10 billion billion. The observed ratio is 1 part in 1 billion. The theory underpredicts the universe by a factor of about 10 billion. This discrepancy has been known for decades and has not gone away despite intense effort. Physicists have explored every loophole in the calculation, every possibility that some overlooked detail might enhance the predicted asymmetry. None of them work. The shortfall is robust. The standard model, as currently understood, simply does not contain enough machinery to produce the universe we observe. That conclusion has serious implications. It means new physics must exist. There must be particles, fields, or interactions beyond the ones in the standard model. They must couple to the early universe in a way that produces additional CP violation, or that triggers stronger departures from equilibrium, or that introduces new mechanisms for baryon number violation. Whatever the answer is, it lies outside the boundaries of current confirmed theory. This is why CERN keeps running. The Higgs discovery completed the standard model, but it also sharpened the question of what comes next. If the standard model cannot explain the asymmetry, then somewhere in the unexplored energy ranges of the LHC, or in even higher energy ranges that future colliders might reach, there should be signs of the missing physics. Heavier particles, new decay channels, subtle deviations in the way known particles behave when probed with sufficient precision. The 2025 baryon result fits into this story as a careful confirmation of where the standard model still works. The known mechanism extends, as predicted, into baryons. It does what it should. And it still does not do enough. The hidden source of the imbalance must therefore lie somewhere physicists have not yet looked closely enough. If the standard model cannot explain the asymmetry, something else can. That something else has not been observed. It exists, currently, only as a set of theoretical possibilities, each of which would extend the known laws of physics in a different direction. None has been directly confirmed, but each one is taken seriously by a major fraction of the global physics community, because the cosmic shortfall demands an answer, and only certain kinds of new physics could plausibly provide one. The most discussed possibility involves heavier versions of particles already known. In several theories, every particle in the standard model has a heavier partner that has not yet been produced in any collider. These partners, if they exist, would carry their own sources of CP violation. They would have been abundant in the very early universe, when energies were high enough to create them. Their decays could have generated baryon excesses far larger than anything the standard model alone allows. Most versions of supersymmetry, a popular framework for extending physics beyond the standard model, fall in this category. A second possibility involves new heavy neutrinos. Ordinary neutrinos are nearly massless and electrically neutral, and they come in three flavors. Some theories propose the existence of much heavier neutrino partners, often called sterile or right-handed neutrinos, which would have been produced in the first instance after the Big Bang and decayed shortly after. Their decays could have favored matter over antimatter through CP-violating channels of their own, producing the imbalance directly. This idea is the basis of a class of theories called leptogenesis, which will appear later in this story. A third possibility involves changes to the Higgs sector. The Higgs boson discovered in 2012 might be the only one of its kind, or it might be part of a larger family of Higgs particles. Extended Higgs theories often introduce new sources of CP violation through the additional fields, and they can also produce strong phase transitions in the early universe, which is exactly what the third Sakharov condition requires. What unites all of these possibilities is a single hard requirement. They must produce effects that the LHC and other experiments could in principle detect. Otherwise, they are untestable, and untestable theories are not science. The current generation of particle physics is, in effect, a vast filter. Each new measurement either confirms a standard model prediction or hints at a deviation. Each deviation is a potential window into the missing physics. Each confirmation, like the lambda B result, narrows the space of possibilities by ruling out scenarios that would have predicted something different. So far, no clear deviation has emerged at the LHC. The Higgs boson behaves as the standard model predicts. The newly observed CP violation in baryons matches the prediction of the existing theory. Searches for supersymmetric partners have come up empty across a wide range of masses. Searches for additional Higgs particles have produced no firm signals. This is not a failure. It is the hard work of elimination. Physics advances by ruling out what is not there as well as by finding what is. Every empty search tightens the net around the eventual answer. But the answer, whatever it turns out to be, is unlikely to come from collisions alone. Some of the most striking experiments in this hunt do not happen on a particle beam at all. They happen with antimatter atoms, captured one at a time, held in place by magnetic fields, and studied with extraordinary patience. The first time anyone trapped an atom of antimatter, it lasted less than a second. The achievement happened at CERN in 2010, inside a different kind of experiment from the high-energy LHC collisions. The facility is called the antiproton decelerator. Where the LHC speeds particles up to nearly light speed, the antiproton decelerator does the opposite. It takes antiprotons produced in collisions and slows them down, cooling them step by step until they are moving slowly enough to be captured and studied. The goal is to create antihydrogen. Ordinary hydrogen is the simplest atom in nature, one proton bound to one electron. Antihydrogen is its antimatter counterpart, one antiproton bound to one positron. If matter and antimatter truly behave identically, then antihydrogen should be a perfect mirror of hydrogen, with the same mass, the same energy levels, and the same response to gravity. Any tiny deviation from that mirror behavior would be a clue to the asymmetry in the early universe. Producing antihydrogen is straightforward in principle. Mix antiprotons with positrons under the right conditions, and they will pair up, just as ordinary matter does. The hard part is keeping the resulting atoms intact long enough to study them. Antihydrogen will annihilate the moment it touches any ordinary matter. It cannot be held in a glass container or measured with conventional instruments. The only way to keep it alive is to suspend it in a vacuum, isolated from all surrounding walls, using a carefully shaped magnetic field that grips the atom by its weak magnetic moment. In 2010, The Alpha collaboration, one of several teams working at the antiproton decelerator, succeeded in trapping 38 atoms of antihydrogen for about 1/6 of a second. It was the first time antimatter atoms had been held still long enough to be studied in any meaningful way. The achievement was incremental, almost humble in its numbers, but it opened a new field of physics. Since then, the trapping has improved dramatically. Modern alpha experiments hold antihydrogen atoms for many minutes at a time. They produce them in batches of hundreds. They can shine lasers on the trapped atoms and measure how they respond, comparing the results to what hydrogen does under identical conditions. Every measurement is a chance to spot a difference. Every difference would be a hint at the asymmetry that built the cosmos. The results so far have been striking in their consistency. Antihydrogen and hydrogen behave the same to the limits of measurement. Their energy levels match, their atomic transitions match, their interaction with magnetic fields matches. If there is a difference between matter and antimatter at this level, it is smaller than current experiments can detect. This is, in its own way, a profound statement. Matter and antimatter, despite the fact that one of them was almost completely erased from the universe, behave nearly identically when held side by side in a laboratory. Whatever broke the symmetry between them in the early universe, it is exquisitely subtle. It does not produce easily visible differences in the products of that long-ago annihilation. It hides. One of the most fundamental tests of all involves something even more basic than energy levels. It involves how antimatter falls. For decades, no one knew which way an apple of antimatter would fall. The question sounds absurd, but it was a serious open issue in physics. Gravity, unlike the other fundamental forces, has never been fully integrated into the framework that describes the rest of particle physics. The standard model handles the strong, weak, and electromagnetic forces with great precision, but gravity stands apart, governed by Einstein's general relativity. The two frameworks have never been unified into a single working theory. Within general relativity, antimatter should fall the same way matter does. Mass is mass, regardless of whether the particles carrying it are made of ordinary stuff or its mirror twin. Gravity pulls on energy, and energy is energy. There is no theoretical room for antimatter to defy gravity in any straightforward formulation. But theory is not measurement, and until very recently, no one had ever directly measured the gravitational behavior of antimatter atoms. Cosmic rays carry antiparticles through the galaxy, but their motion is dominated by electromagnetic forces, not gravity. Particle accelerators produce antiparticles at energies where gravity is negligible. Antihydrogen, neutral, and able to be trapped slowly, was the first system in which a clean gravitational test became possible. Some theorists exploring far-out possibilities had speculated that antimatter might experience anti-gravity. That is, instead of falling down, it might fall up. If that were true, it would explain a great deal about why the early universe ended up with regions of pure matter, since antimatter would have repelled itself away from matter and clustered elsewhere. The idea was always considered fringe, but the data to definitively rule it out did not exist. In 2023, the Alpha collaboration at CERN published the first direct measurement of how antihydrogen responds to gravity. They suspended trapped antihydrogen atoms in a vertical chamber, slowly weakened the magnetic field holding them, and watched where they went. If antimatter fell up, the atoms would drift toward the top of the chamber. If it fell down, they would head toward the bottom. The atoms fell down. The measurement showed that antihydrogen experiences gravity in the same direction as ordinary matter, with a strength consistent with the expected value within the precision of the experiment. The result was not as precise as gravitational measurements done with normal matter, but it was decisive on the question of direction. Anti-gravity, as a property of antimatter, was ruled out. That closed one possible explanation for the cosmic imbalance and reinforced something deeper. Whatever broke the symmetry between matter and antimatter in the early universe, it did not involve gravity behaving differently for the two. The asymmetry must come from one of the other fundamental forces, or from a new force entirely that has not yet been observed. The result also marked another important step in the broader pattern. Every careful test of antimatter, from energy levels to magnetic moments to gravitational behavior, has so far returned the same answer. Matter and antimatter behave the same. The differences, where they exist at all, are tiny and confined to specific decay processes. That makes the original mystery sharper. If matter and antimatter are this similar, how did one of them survive in such overwhelming proportions? The answer must lie in conditions that no longer exist. Conditions that existed only in the first instance after the Big Bang, and that left their imprint behind in ways physicists are still learning to read. Antimatter is not just similar to matter, it is identical to extraordinary precision. Consider one of the most fundamental properties a particle can have. Its magnetic moment. This is a measure of how strongly the particle responds to magnetic fields, and it is determined by the particle's internal structure. For protons, the magnetic moment has been measured for decades to extreme precision. The question for antimatter physics is whether antiprotons have exactly the same magnetic moment, with the opposite sign, as the standard theory demands. The base collaboration at CERN, working alongside Alpha at the antiproton decelerator, has been answering this question for years. They use a technique called penning trap measurement. A single antiproton is captured in a small volume using a combination of electric and magnetic fields. It is held there alone, sometimes for months at a time. Its magnetic moment is measured by watching how it responds to carefully tuned signals. The latest base measurements show that the antiproton's magnetic moment matches the proton's with opposite sign to about a part in a billion. That is the precision of comparing two values and finding them identical to 9 decimal places. If there is a difference between matter and antimatter at the level of a particle's most basic magnetic property, it is below the threshold of one of the most sensitive measurements ever performed. A similar situation holds for mass. Particles and their antiparticles have, as far as anyone has been able to measure, exactly the same mass. Antiprotons weigh as much as protons. Positrons weigh as much as electrons. The matches extend across every known particle-antiparticle pair, with no statistically significant deviation found in any of them. This is striking because the cosmic imbalance is so dramatic. The universe ended up with nearly all matter and nearly no antimatter. If the two were really mirror images in every respect, no mechanism in physics should produce that outcome from a balanced starting point. Yet they appear to be mirror images in nearly every laboratory test scientists can devise. The resolution must lie in the few specific processes where the symmetry is known to break. CP violation in weak decays. The CERN, the B meson, the lambda B. These are the only places where matter and antimatter visibly behave differently, and even there the differences are small. The bulk of physics, including how particles weigh, how they respond to magnetism, how they fall under gravity, treats the two sides of the mirror identically. What this tells researchers is that the explanation for the cosmic asymmetry is going to be subtle. It is not going to come from some dramatic asymmetry between matter and antimatter that should have been visible all along. It is going to come from a careful examination of the few processes where the symmetry does break, combined with conditions in the early universe that no longer exist, and possibly new physics that has not yet been observed. The pattern of laboratory results is consistent. Every careful comparison comes back equal. Every careful measurement of CP violation comes back at the level the standard model predicts. Every search for new physics that would dramatically alter the picture comes back empty, which leaves physicists in a strange position. The cosmos demands an answer that the laboratory has not produced. Something must give. Either the precision of the experiments must continue to improve until a new effect appears, or attention must shift to a different particle entirely, one that has not been studied with the same intensity. That particle might be the lightest, most ghostly thing in the Standard Model. For decades, the experiments came back the same way. Every test of matter and antimatter compared properties and found them equal to the limit of measurement. Every search for CP violation found exactly what the Standard Model predicted. No more, no less. Every hunt for new heavy particles that might explain the imbalance came up empty. The pattern was consistent enough that some physicists began to wonder whether they were looking in the wrong place entirely. The frustration was real. By the early 2010s, the LHC had found the Higgs boson, completed the Standard Model, and begun probing energies far beyond what previous machines could reach. Searches at those energies produced no clear evidence of supersymmetric partners, no extra Higgs particles, no exotic resonances pointing to new physics. The known framework was being confirmed with increasing precision, and the gap between theory and the cosmic imbalance was not closing. Some of the most thoughtful theorists started to refocus. If the asymmetry could not be explained by the heavy quarks and bosons studied at the LHC, perhaps it had been generated by a different family of particles entirely. A family the LHC was not optimized to study, a family known mostly through other kinds of experiments in detectors buried deep underground or filled with thousands of tons of liquid scintillator. That family was the neutrinos. Neutrinos are the strangest members of the Standard Model. They have almost no mass, they carry no electric charge, they interact only through the weak force, which means they pass through ordinary matter almost without notice. Trillions of neutrinos from the closest star pass through your body every second, and almost none of them interact at all. They are nearly ghost-like, and for a long time, they were thought to be entirely massless and entirely uninvolved in the cosmic asymmetry question. That changed in the late 1990s. Experiments studying neutrinos produced by cosmic rays in the upper atmosphere and neutrinos from the sun found that the particles were transforming from one type to another as they traveled. There are 3 known neutrino flavors, called electron, muon, and tau, after the heavier particles they are paired with. The transformation between flavors, called neutrino oscillation, can only happen if neutrinos have some small but non-zero mass. The discovery shook the Standard Model. The original theory had assumed neutrinos were massless. They were not. They were just very, very light. And once they had mass, they joined the family of particles that could, in principle, exhibit CP violation in their oscillations. Matter neutrinos and antimatter neutrinos might not transform between flavors at exactly the same rates. This opened a new front in the search. If CP violation in neutrinos turned out to be large, much larger than the small effect seen in quarks, it could provide the missing source of asymmetry that the cosmic shortfall demanded. The mechanism would not act directly on baryons. It would act on a related family of particles called leptons, which include neutrinos and electrons. But through processes that operated in the very early universe, an asymmetry in leptons could be converted into an asymmetry in baryons. The idea had a name: leptogenesis. And to test it, physicists needed to do something extraordinarily difficult. They needed to catch a particle that almost never interacts, watch it transform in flight, and compare the rate of that transformation in matter and antimatter versions. The first hints from those experiments were starting to come in. To catch a neutrino, you have to be prepared to wait. Neutrinos interact so rarely that most experiments measuring them require enormous detectors filled with hundreds of tons of material, buried deep underground to shield them from cosmic ray noise, and many years of patient observation. Even with all that effort, the number of neutrino interactions recorded in a typical experiment can be just a few thousand per year. Compared to the billions of collisions per second at the LHC, neutrino physics moves at a glacial pace. The reward for that patience is access to something the EC cannot directly provide. A clean look at the lightest particles in the standard model, the ones that may carry the answer to the cosmic asymmetry. Neutrino experiments fire intense beams of these particles across hundreds of miles of solid Earth. Watch them transform from one flavor to another along the way, and compare the rates of those transformations against the rates seen in antineutrino beams. The comparison is the test. If the rates differ, CP violation is present in the lepton sector. If the rates differ enough, the missing piece of the cosmic puzzle might finally be in view. Two major experiments have been pushing this comparison to its limits. The first is called T2K, located in Japan. It generates a beam of neutrinos at a research facility on the eastern coast, and aims it at a detector called Super Kamiokande, buried in a mine on the western coast about 180 miles away. The second is called Nova, located in the United States. It generates its beam at Fermilab in Illinois and sends it to a detector in northern Minnesota, about 500 miles from the source. Both experiments do the same essential thing. They measure how many neutrinos start as one flavor at the source and arrive as a different flavor at the detector. Then they switch to antineutrinos and repeat the measurement. If matter and antimatter neutrinos behaved identically, the rates of transformation would be the same. If CP symmetry is broken in this sector, the rates would differ. The first hints came in the late 2010s. Both T2K and NOVA reported small but persistent differences between neutrino and anti-neutrino oscillation rates. The deviations were not yet large enough to claim a discovery, but they pointed in the same direction. They suggested that CP violation in neutrinos might be substantial, possibly much larger than the corresponding effect in quarks. The implications would be profound. Large CP violation in neutrinos would breathe life into the leptogenesis idea. It would mean the early universe contained a potent mechanism for producing imbalances in lepton populations. Through processes operating at extreme temperatures, those lepton imbalances could be converted into the baryon imbalance physicists actually observe today. The data is still accumulating. Both experiments are continuing to run, refining their measurements, increasing their statistics. A definitive answer is expected from the next generation of experiments, which will combine far larger detectors with more intense neutrino beams. The deep underground neutrino experiment, called DUNE, is being built in the United States with that goal in mind. A similar project called Hyper Kamiokande is under construction in Japan. The hunt has shifted. Where once it focused on heavy quarks and rare meson decays, it now extends across multiple fronts at once. The LHC continues. Antimatter trapping experiments continue. And the ghost particles, lightest of the known family, have stepped into the center of one of the deepest questions in physics. Their behavior in the moments after the Big Bang may have determined everything that followed. The leading idea for explaining the cosmic asymmetry sits one layer beyond the visible standard model. It is called leptogenesis. The name reflects its central claim. The matter excess we see today did not start as a baryon excess. It started as a lepton excess, generated in the very early universe by the decay of a kind of particle that no longer exists in measurable quantities. That excess was then converted, by processes operating at extreme temperatures, into the baryon imbalance that left protons and neutrons behind. The particles at the heart of the theory are heavy neutrinos, not the familiar, nearly massless neutrinos that pass through the planet by the trillion. They're proposed cousins, much heavier, with masses possibly thousands or millions of times greater than the heaviest known standard model particle. These heavy neutrinos would have been produced during the first moments after the Big Bang, when temperatures were high enough to bring them into existence. As the universe cooled, they would have decayed quickly, breaking down into ordinary lighter particles before any of them could survive to the present day. What makes them important is the manner of their decay. If their interactions involve CP violation, the rates at which they produce leptons can differ from the rates at which they produce antileptons. A small asymmetry in those decays would leave behind a tiny excess of leptons over antileptons in the early cosmos. That excess, by itself, would not yet be the matter we see today. The conversion happens later through a class of processes called sphaleron interactions, which can transform lepton excesses into baryon excesses at temperatures above a certain threshold. Once the universe cools below that threshold, the sphalerons shut off, the conversion stops, and the resulting baryon imbalance is locked in. The appeal of leptogenesis is that it ties together several otherwise separate observations. It uses heavy neutrinos, which are predicted by certain extensions of the standard model that also explain why ordinary neutrinos are so light. It uses CP violation in the lepton sector, which the T2K and NOVA experiments are now beginning to detect at their lighter cousins. It uses sphaleron processes, which are already part of the standard model. It satisfies all three Sakharov conditions in a clean and natural way. The challenge is that the heavy neutrinos cannot be produced at the LHC. Their masses are likely far above the energies any current accelerator can reach. Direct discovery is, for now, impossible. The theory must be tested indirectly by measuring the properties of the lighter neutrinos and seeing if they fit the patterns predicted by various leptogenesis models. That is where the next generation of neutrino experiments becomes crucial. If Dooney and Hyperkamiokande detect large CP violation in the lighter neutrinos, the case for leptogenesis strengthens. Specific patterns in how the three neutrino flavors mix can also constrain the parameters of the heavy cousins, even without observing them directly. Combined with measurements of neutrino mass from other experiments, the data could either point convincingly toward leptogenesis or rule out broad classes of versions of the theory. The picture that emerges if leptogenesis turns out to be correct is striking. The matter we are made of did not begin as matter at all. It began as a lepton imbalance, generated by particles that vanished long before the first atoms formed. That imbalance was then translated through cosmic alchemy into the baryons that built every star and every world. To understand how that translation could happen, The story has to move into the first second of the universe. Everything that mattered happened in less time than a blink. The conditions required to produce the cosmic asymmetry, whatever the exact mechanism, existed only during a brief window after the Big Bang. By the time the universe was 1 second old, the temperature had dropped, the density had fallen, and the processes that could rearrange baryon and lepton numbers had largely shut off. Whatever imbalance was going to be locked in had to be locked in by then. This is a strange thing to absorb. The cosmos is now nearly 14 billion years old. Stars have lived and died. Galaxies have merged. Planets have formed and cooled. None of it, however, has changed the fundamental ratio of matter to photons. That ratio was set during the first second, possibly during the first tiny fraction of a second, and it has remained essentially fixed ever since. Every atom you see is descended directly from the survivors of that early moment. The reason for the lock-in is straightforward in physics terms. The processes capable of changing baryon number, like sphalerons, only operate at temperatures above about 100,000 billion degrees. That temperature was reached only in the very early universe. Once the universe cooled below it, sphalerons stopped functioning. After that point, the total baryon number became a conserved quantity. It could be redistributed in space, concentrated into galaxies, or thinned out in voids, but it could not be increased or decreased in total. The same applies to the heavy particles thought to drive baryogenesis or leptogenesis. They could only have existed at the highest temperatures. As the universe cooled, they decayed away. Their imprint on the cosmos, the asymmetry they generated, became fixed. The mechanism shut down behind them, like a chemical reaction that completes and then cannot run in reverse. This is what makes the search so difficult. The mechanism is gone. The conditions cannot be recreated, even at the LHC, because no terrestrial machine can match the temperatures and densities of the first cosmic instant. What remains is the residue, the leftover ratio, the fact of survival itself. To work backward from that residue to the original mechanism requires combining laboratory measurements with cosmological data, theoretical models, and the careful elimination of possibilities that fail to fit. The very early universe was, in a real sense, a one-time experiment. It ran once. It produced one outcome. It cannot be repeated. The only way to learn what happened is to read the evidence it left behind, and to use that evidence to build models constrained tightly enough to match every measurement. The cosmic microwave background provides one important set of constraints. It tells physicists about the density of matter, the geometry of space, the temperature variations from the very early cosmos. The abundance of light elements like helium and deuterium provides another set. They were forged the first few minutes after the Big Bang, and their proportions depend sensitively on the matter content of the universe at that time. Observations of large-scale galaxy structure provide a third constraint. The way galaxies cluster encodes information about how matter began to condense from the primordial soup. All of these data, combined with particle physics measurements at colliders and underground neutrino observatories, narrow the space of possible mechanisms. They have not yet identified the answer. They have ruled out many candidates and pointed toward others. One of the most natural candidates involves a sudden change in the universe itself. The early universe was not always the same. It went through changes, sudden ones. Moments when the very nature of space itself transformed from one configuration into another. These events are called phase transitions, and they are familiar in everyday life in much smaller forms. Water freezing into ice is a phase transition. Iron becoming magnetic as it cools is a phase transition. The structure of the material changes abruptly when conditions cross certain thresholds, even though the underlying particles remain the same. The early universe went through phase transitions of its own, but on a far grander scale. The most consequential one is called the electroweak phase transition. It happened when the universe was about a trillionth of a second old, and the temperature dropped below a critical value. Before that moment, the electromagnetic force and the weak nuclear force were unified into a single force, called the electroweak force. After that moment, they separated, and the Higgs field condensed into the form it has today, giving the known particles their masses. This transition is important for the matter-antimatter question, because it provides a natural setting for the third Sakharov condition. During a phase transition, the universe is dramatically out of thermal equilibrium. Reactions that would normally cancel each other out can leave behind net effects, including potentially a baryon excess. If the transition is sharp enough, with enough departure from equilibrium, it can lock in an asymmetry that would otherwise dissolve. A class of theories called electroweak baryogenesis explores this possibility. They propose that the electroweak phase transition was strong enough, and CP violation was large enough at that moment, to produce the matter excess directly. The mechanism would have operated entirely within or near the standard framework, without requiring heavy neutrinos or other exotic particles. It would just require the phase transition to behave differently than the standard Higgs theory predicts. The catch is that the standard Higgs theory predicts the electroweak phase transition was actually quite gentle. A smooth crossover, rather than a sharp break. That gentle transition would not produce enough departure from equilibrium to generate the observed baryon imbalance. For electroweak baryogenesis to work, the Higgs sector would need to be more complex than what has been observed so far. Additional Higgs particles or modified couplings would need to make the transition sharper. This is one of the reasons CERN keeps probing the Higgs boson with increasing precision. Every measurement of how the Higgs interacts with other particles, every search for additional Higgs-like particles, tests whether the simple version of the theory is the full story. So far, the Higgs has behaved exactly as the minimal standard model predicts. No clear evidence of additional Higgs particles has emerged. The window for electroweak baryogenesis to work in its simplest form is narrowing, though not yet closed. If electroweak baryogenesis turns out to be wrong, the answer falls back to leptogenesis or another mechanism operating at higher energies. If it turns out to be right, the missing physics is much closer to being directly observable, and the next generation of experiments at the LHC and its successors should reveal it. The phase transition itself, whether or not it generated the asymmetry, was one of the most consequential events in the history of the cosmos. It set the masses of the known particles, defined the structure of matter, and determined the rules by which the universe would evolve from that moment forward. And it happened only once. The Higgs boson was supposed to be the final piece. When it was discovered at CERN in 2012, after a search that had lasted nearly 50 years, the announcement felt like a closing chapter. The Standard Model, the most thoroughly tested theory in physics, had predicted the existence of a particle that gave other particles their mass through interaction with a special field that pervaded all of space. Decades of indirect evidence had pointed to it. The LHC was built in part to either find it or rule it out. The discovery confirmed that the Higgs field was real, that the mechanism for giving particles mass operated as predicted, and that the Standard Model framework was complete in its essential structure. There were no obvious holes left in the theory. Every particle the framework required had now been observed. For some questions, this was a triumph. For the matter-antimatter question, it was a problem. The reason has to do with how electroweak baryogenesis depends on the Higgs sector. For the simplest version of the theory to produce the observed baryon imbalance, the Higgs phase transition would have needed to be a strong, abrupt one. The strength of that transition depends on the mass and interactions of the Higgs particle. With a mass around the lower end of the predicted range, the transition could have been violent enough to drive the asymmetry. With a mass higher up, the transition would be too gentle. The Higgs turned out to have a mass right in the middle of the range, but with properties that suggested the transition would be too smooth to produce sufficient asymmetry on its own. The simplest version of electroweak baryogenesis was effectively ruled out by the Higgs measurement itself. A discovery that completed one part of physics simultaneously closed a door on one of the leading explanations for why matter exists. This was not the end of the story. Modified versions of electroweak baryogenesis remain viable, especially those that introduce additional Higgs particles or extra fields that modify the transition. Searches for those additional particles are ongoing at the LHC. They have not produced definitive evidence yet, but the searches are far from complete. The high luminosity LHC upgrade, which will increase the collision rate by roughly a factor of 10, will significantly expand the ability to detect rare or weakly interacting new physics. The discovery also reshaped the question in a deeper way. By confirming that the Standard Model is complete and self-consistent, it forced the field to confront the gaps in the framework more directly. The Standard Model does not explain why matter dominates. It does not explain dark matter. It does not include gravity. It does not explain why the masses of the known particles take the specific values they do. These are not minor refinements. They are fundamental holes in our understanding of nature. The Higgs, in other words, was both an answer and a beginning. It closed one search and opened a wider field of inquiry. The work that followed has been less about confirming the existing framework and more about probing for the hints of what lies beyond it. For the antimatter question, the most active probing now happens at the boundary where the standard model's predictions can be tested with the highest precision. Every percent level deviation in any measurement is a potential signal. Every empty search narrows the space of possibilities further. And the search has begun to extend in directions the LHC was not built for. The next generation of particle physics is, in a sense, a campaign of elimination. The standard model is so well confirmed that any new physics has to hide in places where it has not yet been looked closely enough. Those places fall into a few categories. Higher energies, which only future colliders can reach. Rarer processes, which require more collisions to detect. Lower energy precision measurements, where small deviations from theory can reveal heavy particles whose direct production is impossible at current machines. Cosmological observations, which probe conditions that no laboratory can recreate. The LHC has been extending the high-energy frontier for over a decade. Searches for supersymmetric partners have ruled out their existence below increasingly higher mass thresholds. Searches for additional Higgs particles have done the same. Searches for new heavy particles that might modify CP violation have continued without producing definitive signals. None of this has falsified the broad ideas. It has narrowed where they could possibly hide. The high luminosity upgrade, expected to begin operating in the late 2020s, will multiply the LHC's collision rate substantially. That increase translates directly into sensitivity to rarer processes and to slight deviations in the behavior of known particles. Effects that are currently buried in statistical noise will become visible. The lambda BCP violation result observed in 2025 will be measured to higher precision, allowing physicists to check whether the size of the effect agrees with the standard model prediction at finer and finer levels. Any disagreement, no matter how small, would be a window into new physics. Other approaches operate on different principles. Electric dipole moment measurements, performed in tabletop atomic physics experiments, look for tiny asymmetries in the distribution of charge inside individual particles. These asymmetries would be amplified if heavy particles producing CP violation existed at higher energies, even if those particles are too heavy to be produced directly. The current limits are extraordinarily tight. The neutron, for example, has been shown to have an electric dipole moment smaller than about 10 to the minus 26 times the basic units physicists use. That precision is so high that it constrains entire classes of new physics models more tightly than any direct collider search. Underground neutrino experiments continue to refine measurements of CP violation in oscillations, with Dune and Hyper Kamiokande expected to provide definitive answers within the next decade. Searches for proton decay, which would be a direct signature of baryon number violation, continue in the same large detectors. Searches for neutrinoless double beta decay, which would reveal the nature of neutrino mass and constrain leptogenesis models, are operating at multiple facilities around the world. Cosmological observations contribute as well. Surveys of the cosmic microwave background continue to refine measurements of cosmological parameters, including the baryon density and the early universe conditions. Future observations may detect gravitational waves from the electroweak phase transition or earlier events, which would directly probe the violent moments when the asymmetry was likely generated. None of these efforts is guaranteed to succeed. Physics has never been able to predict in advance when a major discovery will arrive. But the combined assault, working from many directions at once, makes the next decade likely to be decisive. Either the answer to the matter-antimatter problem will emerge from one of these channels, or the existing models will be ruled out so comprehensively that the field will need to start from genuinely new theoretical foundations. Some of the most haunting evidence comes from a place no terrestrial experiment can reach. If antimatter survived somewhere in the universe, the night sky would be glowing with the evidence. When matter and antimatter meet, the annihilation produces a very specific signature. High-energy gamma rays at distinctive energies, especially around 511,000 electron volts. The energy released when an electron annihilates with a positron. If there were regions of the universe dominated by antimatter, the boundaries between those regions and ordinary matter regions would be glowing with this gamma ray signature. The brightness would be enormous, visible across cosmological distances, and impossible to miss. The sky has been searched carefully for this kind of signature for decades. Multiple gamma-ray telescopes, in space and on the ground, have surveyed the heavens looking for the telltale glow of large-scale annihilation. The result has been clear. There is no such glow at the levels expected from antimatter regions of significant size. The universe, on the largest scales we can observe, is made of matter. The antimatter is not hiding behind some cosmic curtain, waiting to be found. This conclusion is robust. It has been tested in multiple ways with different instruments over many years. Every observation comes back consistent with a matter-dominated universe. If there are pockets of antimatter, they must be either extraordinarily small or so distant that they lie beyond the observable cosmos. Neither possibility helps explain the observed asymmetry, which would still need to have been generated by some early universe mechanism. The search for primordial antimatter has continued in more focused ways. The alpha magnetic spectrometer, called AMS-02, was installed on the International Space Station in 2011 and has been collecting data ever since. Its purpose is to measure the composition of cosmic rays with unprecedented precision, including the rare antimatter components. Most antimatter in cosmic rays is produced when high-energy particles collide with interstellar gas, generating positrons and antiprotons as ordinary byproducts. AMS-02 measures these and confirms they appear in roughly the expected amounts. What AMS-02 looks for, beyond the ordinary signal, is something far more striking: antihelium nuclei. A helium nucleus contains 2 protons and 2 neutrons bound together, and the corresponding antinucleus would contain 2 antiprotons and 2 antineutrons. Producing such an antinucleus through ordinary cosmic ray interactions is extraordinarily improbable. The chance is so small that any detection of antihelium in cosmic rays would be a major signal that something unusual is producing it. For more than a decade, AMS-02 has reported a small number of candidate events that look like anti-helium. The number is too few to claim a discovery, but too many to easily explain through known processes. The collaboration has been carefully analyzing these events, looking for systematic errors that might mimic the signal. As of the most recent reports, the candidates remain. Their origin is unknown. Several explanations are possible. They could be artifacts of detector limitations, which would dissolve under more careful analysis. They could be from rare astrophysical processes not yet fully understood. Or they could be the first hints of antimatter regions or antimatter producing objects somewhere in the galaxy or the wider cosmos, which would change the picture of the asymmetry significantly. The data continues to accumulate. A MS-02 was approved for an extended mission, and the candidate events are being scrutinized closely. A definitive answer will require either a clear explanation for the signal or a confirmed detection of anti-helium at higher statistical significance. Either way, the broader conclusion holds. The universe at large is made of matter. The antimatter is essentially gone. Whatever happened in the first second of cosmic history, it acted everywhere, at the same time, and produced the same outcome on every scale humanity has been able to observe. That uniformity is itself a powerful clue. The matter-antimatter asymmetry is not a local feature. When astronomers map the distribution of galaxies across billions of light years of space, they find the same composition everywhere. Hydrogen, helium, and the heavier elements forged in stars. No region appears to be made predominantly of antimatter. The cosmic background radiation, which fills the universe in every direction, shows no asymmetric heating that would result from boundaries between matter and antimatter regions. Everything points to a single conclusion. The mechanism that produced the imbalance acted uniformly throughout the early universe. This uniformity is a strong constraint on what the mechanism could have been. It must have operated at a scale large enough to affect every region simultaneously, or it must have been a property of the laws of physics themselves, applied identically wherever the early universe was hot and dense. Local fluctuations or random variations would have produced regions with different baryon to photon ratios, possibly even regions where antimatter dominated. No such variations have been observed. The most natural way to achieve this uniformity is for the mechanism to be a fundamental feature of particle physics, operating everywhere the conditions allowed. Whether it was leptogenesis driven by heavy neutrinos, electroweak baryogenesis driven by a strong phase transition, or some other process, the mechanism would have run in every cubic centimeter of space at the same time, producing the same imbalance everywhere. Once the conditions ended, the imbalance was locked in globally. This picture has a strange beauty to it. The universe, at its hottest and densest moment, behaved with a kind of thermal democracy. Every region was subject to the same physical laws, the same temperatures, the same processes. The asymmetry that emerged was a property of those laws under those conditions, not a consequence of local accidents or initial variations. It also has a cold finality. Whatever happened in these first instants determined the entire chemistry of the future cosmos. Every star that would ever form, every planet that would ever cool, every organism that would ever live, all of it was shaped by a number set in a fraction of a second, nearly 14 billion years ago. There were no second chances, no reversals, no alternative outcomes possible after that moment. This is part of what makes the question so compelling. The matter-antimatter asymmetry is not just a curiosity of particle physics. It is a fingerprint of the deepest moment of the universe, preserved across all of cosmic history, encoded in the existence of every atom. To understand it is to understand something fundamental about how the cosmos chose its own composition. The lambda B result observed in 2025 fits into this picture as a small but real piece of evidence. It confirms that CP violation can occur in the family of particles that ended up dominating the cosmos. It does not yet identify the dominant mechanism that produced the imbalance, but it shows that the kind of asymmetry needed is, at least in part, present in the laws of physics as they operate today. The same kind of asymmetry, amplified by conditions in the early universe and possibly enhanced by physics not yet observed, could have generated everything that followed. The uniformity of the cosmic imbalance also rules out certain explanations. Theories that invoke local accidents, rare statistical fluctuations, or initial conditions specific to a single region of space cannot account for what is observed. The mechanism had to be global. It had to be universal. It had to be a property of physics itself. That requirement narrows the search significantly, and the next decade of measurements will narrow it further. The lambda B discovery is not an answer. It is a refinement of the question. For 60 years, physicists had been hunting for CP violation in baryons without success. Theory said it should exist. The standard model required it. Experimental detection, however, had remained out of reach until enough data accumulated and the analysis techniques became sensitive enough. The 2025 result closed that gap. It confirmed that the predicted asymmetry exists in the family of particles that make up everything around us. What the result tells the field is several things at once. First, it confirms that the standard model's mechanism for CP violation extends, exactly as predicted, into baryons. There is no surprise in the size of the effect. There is no anomaly suggesting new physics is hiding inside the lambda B system. The known framework continues to work where it has been tested. Second, it sharpens the cosmic shortfall. The standard model's predictions are now confirmed in mesons and baryons. The size of those predictions, when projected onto the early universe, falls short of explaining the observed matter-antimatter imbalance by a large factor. That shortfall is now even more clearly established. Whatever new physics is needed, it must lie outside the channels currently being tested at this level of precision. Third, it gives experimenters a new platform for further searches. The lambda BCP violation will now be studied in detail. Different decay channels will be measured. Comparisons across multiple baryons will be made. Each measurement is a chance for the data to deviate from the standard model prediction. Each deviation, no matter how small, would be a hint of new physics. The 2025 discovery opens a sector of particle physics that was previously closed to careful experimental study. Fourth, it strengthens the case for continuing investment in the LHC and its successors. The result was made possible by the enormous data sets collected over years of operation, combined with sophisticated analysis techniques that took years to develop. That kind of careful, patient work depends on long-term funding and stable scientific institutions. The discovery validates the strategy of pursuing rare processes with high statistics, even when individual measurements take a decade or more to produce results. Within the broader hunt for the matter-antimatter mechanism, the 2025 result occupies a specific position. It is a confirmation, not a revolution. It rules out certain extreme deviations from the standard model in the baryon sector, while leaving the central mystery untouched. The hidden source of the cosmic asymmetry is still hidden. The search continues. Some physicists have framed the result as a kind of milestone. After more than half a century of work, every major prediction of CP violation in the standard model has now been observed somewhere. Carnes, B mesons, and lambda B baryons all show the effect. The theory has been validated in every channel where it can currently be tested. The fact that this complete validation still leaves the cosmic asymmetry unexplained makes the case for new physics nearly inescapable. The natural next question is where that new physics lives. The LHC has been searching for it for over a decade and has not found it directly. The high luminosity upgrade will extend the search by roughly another order of magnitude in sensitivity. Beyond that, future colliders are being designed to push to higher energies still. Underground neutrino experiments will probe the lepton sector. Tabletop precision experiments will continue to refine their limits on electric dipole moments and other rare effects. The search has many fronts. Each one tightens the constraints. Each one narrows the space where the answer can hide. The next 10 years will determine the shape of the answer. Several major experimental programs are reaching maturity. The high luminosity LHC will begin full operation in the late 2020s, increasing collision rates substantially and dramatically improving sensitivity to rare processes. Searches for new heavy particles, additional Higgs particles, and small deviations in known processes will all benefit. Within the decade, the HLLHC will either produce evidence of physics beyond the standard model or rule out wide classes of theories that have been considered leading candidates for decades. The Dune experiment in the United States is scheduled to begin operation in the late 2020s, with full physics running in the early 2030s. It will measure CP violation in neutrino oscillations with unprecedented precision over a baseline of nearly 800 miles between the source at Fermilab and the detectors in South Dakota. Hyper Kamiokande in Japan will operate on a similar timeline, measuring the same physics with different systematic strengths. Together, they will determine whether neutrinos exhibit large CP violation, providing strong evidence for or against leptogenesis. Electric dipole moment experiments continue to push their precision higher. New techniques using cold molecules and trapped ions promise to improve current limits by factors of 10 or more in the next decade. Any positive signal in these experiments would be a major indication of physics beyond the standard model, with direct implications for the matter-antimatter question. Cosmological surveys are also reaching new levels of precision. Future cosmic microwave background experiments will detect, or strongly constrain, gravitational waves from the early universe. Such waves could provide direct evidence of the electroweak phase transition or earlier events that might have generated the asymmetry. Galaxy surveys will refine measurements of cosmic structure and the baryon density to higher precision. Antimatter experiments at CERN will continue. Improvements in trapping and cooling will allow more detailed comparisons of antihydrogen with hydrogen, and similar comparisons may be extended to heavier antiatoms in the future. Any small deviation from perfect mirror behavior would be a profound discovery. By the mid-2030s, the combined results from all these efforts will either point clearly toward a specific mechanism or rule out so many possibilities that the field will need to undertake a major theoretical reassessment. Either outcome would be a significant step forward. Discovery of a clear signal would launch a new era of physics. Comprehensive elimination of leading theories would force a return to fundamentals, with the next generation of theorists working from a much more constrained set of options. The pace of this kind of work is slow by everyday standards, but rapid by historical standards. The matter-antimatter problem has been recognized for more than 70 years, and meaningful progress has accumulated steadily over that time. The first half of the search was driven by surprise discoveries like the kaon CP violation in 1964 and the neutrino mass result in the late 1990s. The current half is driven by careful, systematic measurement at increasing precision, combined with theoretical work that explores the implications of every new datum. The 2025 Lambda B result fits squarely in this current pattern. It was not a surprise. It was a confirmation achieved through patience and scale. The next breakthroughs may come the same way, or they may come unexpectedly, from a measurement nobody saw coming. Either possibility is consistent with the history of the field. What does seem certain is that the question itself has narrowed. The space where the answer can hide is smaller than it was a decade ago. And it will be smaller still in another 10 years. The cosmic asymmetry may be a clue to a question even larger than itself. CP symmetry. The rule the universe was supposed to follow is one of 3 related symmetries in particle physics. The other 2 are time reversal symmetry, called T, and the combination of all 3, called CPT. The CPT theorem, one of the most fundamental results in modern physics, states that any reasonable theory of particles must respect the combined CPT symmetry exactly. This has been tested with extraordinary precision and has held up in every measurement. The CPT theorem has a consequence that connects directly to the matter-antimatter question. If CPT is exact and CP is broken, then time reversal symmetry must also be broken. The amount of T violation must equal the amount of CP violation, so that their combination preserves the overall CPT symmetry. This means every observation of CP violation is also an observation of an asymmetry in time itself. That conclusion has strange implications. It means that at the level of fundamental physics, time has a direction built into it. Not just the everyday direction provided by entropy and the second law of thermodynamics, but a direction that shows up in the basic interactions of particles. The arrow of time is not purely a statistical phenomenon. It is at some level written into the laws themselves. This connection between CP violation and the arrow of time is one of the deepest features of modern physics, and it remains poorly understood. The size of the time asymmetry is small, just like CP violation, but its presence is undeniable. Why nature chose to break these symmetries, and why it did so by exactly the amounts it did, is unknown. Some theorists have suggested that the answer to the matter antimatter asymmetry and the answer to the deeper question of why these symmetries are broken are linked. The mechanism that produced matter would, in this view, also be the mechanism that gave time its direction at the fundamental level. Both phenomena would be consequences of the same underlying physics, possibly involving fields or particles that have not yet been observed. Other theorists pursue different avenues. Some explore whether CP violation is connected to the structure of space-time itself, possibly through quantum gravity effects that cannot be tested at current energies. Some explore whether it is connected to the cosmological initial conditions, the specific configuration the universe started in. Some explore connections to dark matter or dark energy, the two unexplained components of the cosmic energy budget. None of these directions has produced a definitive answer. They remain open lines of theoretical investigation, each with its own arguments and counter-arguments. What unites them is the recognition that CP violation is too important to be a footnote. The fact that the universe favored matter is a major feature of reality, and the explanation for it must connect to something deep in the structure of physics. The lambda B discovery, the neutrino oscillation hints, the anti-hydrogen measurements, the cosmic ray searches, all of them are pieces of a much larger puzzle. The puzzle is not just about the relative numbers of two kinds of particles in the early universe. It is about why the laws of physics were structured in a way that allowed those numbers to be different at all. Solve the cosmic asymmetry, and you may solve a question about time itself. You are made of leftover survivors. That phrase is not poetic, it is literal. Every atom in your body traces back, through chains of stellar births and deaths and gravitational collapses, to baryons that emerged from the early universe with that 1 in a billion advantage over their antimatter twins. The carbon in your cells, the iron in your blood, the calcium in your bones, all of it was forged inside stars from hydrogen and helium that themselves were produced in the first minutes after the Big Bang, from baryons that were already there. If the cosmic asymmetry had been smaller, none of those stars would have formed. The matter density of the universe would have been too low for gravitational collapse to produce the dense regions where nuclear fusion can ignite. If the asymmetry had been larger, the universe would have collapsed into black holes too quickly for stars and planets to evolve. Your existence depends on the fact that the imbalance fell within a narrow window. That window was set in the first second of cosmic history, by a mechanism nobody yet understands. This is one of the more humbling realizations modern physics offers. The chain of conditions that allowed you to exist runs through the very deepest layers of the universe, all the way back to the moment when the basic chemistry of reality was decided. You are not just made of star stuff, as the old phrase has it. You are made of survivors, particles that escaped a near total annihilation by a factor that shapes everything you have ever seen. The search for the explanation is, in a real sense, a search for your own origin. Not in the biological sense, but in the most fundamental physical sense possible. Why is there matter? Why is there a universe to live in? Why does anything exist at all? These are not philosophical abstractions. They are questions that modern physics has translated into specific, measurable problems, and that experiments at CERN and elsewhere are working to answer. The progress so far has been substantial. The basic framework of CP violation has been established. The Standard Model's contribution has been measured and shown to be insufficient. The places where new physics could plausibly hide have been narrowed. The 2025 Lambda B result is the most recent step in this long process, confirming that the asymmetry is present in the family of particles that make up the visible cosmos, including the particles that make up you. What comes next is uncertain, but the pace of progress is real. Within a decade or two, the answer is likely to come into clearer view, either through a new discovery at the LHC or its successors, or through a breakthrough in neutrino physics, or through a cosmological observation that constrains the early universe in a new way. The mechanism that produced the matter you are made of will probably be identified in the lifetime of some of the people reading this. For now, the answer remains hidden. But the search itself is one of the great scientific endeavors of this era. It connects the smallest scales of physics, the interactions of individual particles, to the largest, the composition of the entire cosmos. It bridges laboratories underground with observations across billions of light years. And it points toward an answer that, when found, will be one of the most fundamental insights humanity has ever achieved. You exist because of a mistake the universe made, or perhaps a feature it always had. Either way, that fact is worth understanding. Some physicists believe the matter-antimatter problem connects to other unsolved mysteries. The Standard Model leaves several major questions unanswered. Beyond the cosmic asymmetry, it does not explain dark matter, the invisible substance that outweighs ordinary matter by a factor of about 5 and shapes the gravitational structure of galaxies. It does not explain dark energy, the still mysterious form of energy that is causing the expansion of the universe to accelerate. It does not explain why the masses of the known particles take the specific values they do. It does not include gravity. And it does not explain the asymmetry between matter and antimatter. The hope, pursued by a significant fraction of theoretical physicists, is that some of these mysteries are connected. A single extension of the Standard Model, if found, might address several of them at once. Theories that introduce heavy neutrinos for leptogenesis, for example, can also explain why the lighter neutrinos have such small masses. Theories that introduce supersymmetric partners can provide candidates for dark matter while also enhancing CP violation in ways that might help baryogenesis. Theories that include additional Higgs fields can both modify the electroweak phase transition and provide new sources of CP violation. If one of these unified theories turns out to be correct, the matter-antimatter asymmetry would not be an isolated puzzle. It would be one consequence of a larger structure that also explains other major features of the cosmos. The discovery of any one piece of that structure would bring with it implications for the others. The search for such a theory has been one of the central activities of theoretical physics for decades. Many candidates have been proposed. Few have made unique, testable predictions that distinguish them clearly from the standard model in ways that experiments have been able to confirm. Each generation of accelerators and detectors has tested some of these candidates and ruled out the simplest versions, while leaving more elaborate variations untested. The most ambitious frameworks, sometimes called grand unified theories, propose that the strong, weak, and electromagnetic forces unify at extremely high energies. If true, the unification would also unify the matter content of the standard model in ways that could naturally produce baryon number violation and CP violation in the early universe. These theories typically predict that protons should decay, although extremely rarely. Searches for proton decay have been running for decades in large underground detectors, and so far have produced no clear signal. The current limits on proton lifetime rule out the simplest versions of grand unified theories, but leave more sophisticated versions viable. The interplay between theory and experiment in this area is delicate. Each round of experimental results forces theorists to refine their models, eliminating ones that conflict with data and elaborating ones that survive. Over time, the surviving theories tend to become more complex, requiring more parameters and more specific assumptions to remain consistent with observations. This is sometimes seen as a worrying trend, suggesting that the field is heading toward theories that are too flexible to be cleanly tested. Other physicists view it as the natural process of refinement, with the eventual answer likely to require some level of sophistication that the simplest models cannot capture. The matter-antimatter problem sits within this larger landscape. Its eventual solution may come from a unified framework that addresses several mysteries together, or from a more focused mechanism specific to the asymmetry alone. Either way, the answer is likely to reshape parts of the broader picture. There is a possibility worth confronting. The matter-antimatter asymmetry might not have a clean, complete explanation that is accessible to laboratory experiments. The mechanism may have operated at energies far above anything human technology can ever reach. Its signature in the present universe may be limited to the residue itself, the cosmic baryon density, with no accessible experimental probes that can distinguish among different theoretical proposals. This is not the most likely outcome, but it is possible. If the asymmetry was generated at the highest energies, near the scale of grand unification or quantum gravity, then no foreseeable accelerator will ever be able to produce the relevant particles directly. The constraints on the mechanism would have to come entirely from indirect effects. from precision measurements of low energy physics that are sensitive to the high energy theory through subtle effects, and from cosmological observations that probe the early universe's overall behavior. In such a case, the answer might be narrowed, but never fully confirmed. Multiple theoretical proposals could remain consistent with all available data, with no clean way to distinguish between them. The search would not fail exactly. It would arrive at a kind of permanent partial answer, where the broad framework was understood, but the specific details remained ambiguous. Many physicists find this prospect uncomfortable. Science aspires to definite answers, and the matter-antimatter problem is the kind of question that seems to demand one. Nevertheless, the possibility that the answer lies forever beyond direct testing is not something that can be ruled out by determination alone. The universe owes us no guarantees about what we can or cannot eventually understand. This concern is partly mitigated by the breadth of the search. Even if the highest energy mechanism is inaccessible, lower energy effects may still be detectable. Leptogenesis, for example, involves heavy neutrinos that may be too heavy to produce directly, but the lighter neutrinos that are connected to them are accessible to experiments like DUNE and Hyper-Kamiokande. Measurements of the lighter sector can constrain the parameters of the heavier sector indirectly. Similar logic applies to other mechanisms. The cosmological observations provide another avenue. Future detection of gravitational waves from the early universe, for example, could provide direct information about the conditions during the relevant cosmic epoch. The amplitude and spectrum of such waves would depend on the details of the asymmetry generating mechanism, providing a way to distinguish among proposals even if the relevant particles are not directly producible. A third avenue is the precision measurement of known properties. If a particle in the standard model has a property whose value depends sensitively on what happens at higher energies, then measuring that property to high precision can reveal indirect signs of the high energy physics. Electric dipole moments are one example. Rare decay rates are another. Anomalous magnetic moments are a third. Each of these areas has been the subject of intense experimental activity, and each has the potential to reveal a deviation from standard model predictions that would point toward new physics relevant to the matter-antimatter question. The search for the cosmic asymmetry's origin is, in this sense, more secure than it might at first appear. Even if the most direct path is blocked, multiple alternative paths remain available. The answer may take longer to converge than physicists hope, but the framework for finding it is broad and well established. What seems certain is that the question itself will continue to drive scientific progress for decades to come. The hunt for why matter exists is one of the great endeavors of modern science. It has occupied thousands of physicists across multiple generations. It has driven the construction of some of the largest scientific instruments ever built. It has produced discoveries that reshaped fundamental theory. From the kaon-CP violation in 1964, to the Higgs boson in 2012, to the lambda b CP violation in 2025. Each discovery has been a step, sometimes incremental, sometimes transformative, in a continuing campaign to understand why the universe is the way it is. The search has also produced a deep appreciation for how the universe actually works at its smallest scales. The Standard Model, built piece by piece over the past century, is now one of the most successful scientific theories in history. It predicts the behavior of particles and forces with extraordinary accuracy across an enormous range of energies. The fact that it cannot fully explain the matter, antimatter asymmetry, is not a failure of the framework. It is a sign that there is more to learn, more to discover, more to understand. The matter-antimatter problem also illustrates the way modern physics works. No single experiment, however well designed, can answer such a deep question on its own. The answer, when it comes, will emerge from the combined results of many experiments operating across many domains. Particle colliders, underground neutrino detectors, tabletop precision measurements, cosmological observations. Each provides a different kind of information, and each contributes to the eventual resolution. This collaborative, multi-front approach is part of why progress can sometimes seem slow. The kinds of questions modern physics confronts are too big for any single team or single technique to address completely. They require sustained effort across decades, with each new generation of physicists building on the work of those who came before. The Lambda B result was made possible by data collected over more than a decade at a machine that took decades to build, analyzed by techniques that took years to develop in the context of a theoretical framework that has been refined over generations. The slow pace can be frustrating. It can also be understood as a sign of the depth of the questions being asked. Easy questions get answered quickly. Hard questions take longer. Questions about why the universe exists at all are at the upper end of the difficulty spectrum. That they are being addressed at all, in concrete and measurable ways, is itself a remarkable feature of modern science. For the wider public, the search may seem distant from everyday life. The particles being studied are exotic. The energies involved are extreme. The conditions being investigated existed only in the first second of the universe, and will never be encountered again outside laboratories. Yet the eventual answer will speak to one of the most basic questions any thinking being can ask. Why is there something rather than nothing? The matter-antimatter asymmetry is not the whole answer to that question, but it is a substantial part of it. The work continues, new data accumulates, new analyses are performed, new theoretical proposals emerge and are tested. Each year brings the field a little closer to the answer, even when the progress is not announced in headlines. The search is patient, careful, and methodical, as the best science often is. And the deepest implication of what is being learned is one that physics has not quite finished absorbing. The universe came close to having no story to tell. In the first instance after the Big Bang, the cosmos was almost balanced perfectly between matter and antimatter. The two populations should have annihilated each other completely, leaving behind a sterile expanse of cooling radiation and nothing else. No stars, no galaxies, no planets, no chemistry, no life, no minds, no questions. The entire history of the universe, as it actually unfolded, was contingent on a tiny imbalance that nobody fully understands. That imbalance was about 1 part in 1 billion, a number small enough to seem like rounding error in any everyday calculation, large enough to determine the entire future of reality. Every star you have ever seen, every world that orbits one, every cloud of gas drifting between galaxies, all of it descends from the small fraction of matter that survived the Great Annihilation. The cosmos is a thin scattering of leftovers, distributed across an immense volume of nearly empty space, lit by the slow burning of those leftovers in stars. The story of how that imbalance came to be is still being written. 60 years of research have established the basic outline. CP symmetry, the rule that should have kept matter and antimatter perfectly equal, is broken in particle physics. The breaking is small in known channels, far too small to explain the cosmos by itself, but it is real and now confirmed in the family of particles that make up everything visible. Beyond the known framework, additional sources of CP violation must exist, possibly hidden at energies higher than current experiments can directly probe. The search for those additional sources is one of the central activities of modern physics. The 2025 Lambda B discovery was a milestone in that search. After more than 50 years of effort, CP violation was finally observed in a baryon, the family of particles that includes protons and neutrons. The observation confirmed the Standard Model's predictions in a sector where they had not previously been directly tested. It also sharpened the case that the cosmic shortfall requires new physics, since the predicted effect, while now confirmed, is still too small to explain the observed imbalance. The work continues across many fronts. The high luminosity LHC will refine the baryon measurements and search for new heavy particles. Dune and Hyperchemiocandair will determine whether neutrinos exhibit large CP violation, providing strong evidence for or against leptogenesis. Antimatter experiments at the antiproton decelerator will test, with increasing precision, whether matter and antimatter behave identically in fundamental ways. Cosmological observations will probe the conditions of the very early universe more deeply. Each of these efforts is a piece of the larger puzzle, and the combined results over the next decade are likely to bring the answer significantly closer. Whatever the answer turns out to be, it will speak to one of the deepest features of reality. The universe favored matter by a tiny margin, for reasons that are still partly hidden. That preference is the foundation on which everything else has been built. The atoms in your hands, the stars in the sky, the slow turning of galaxies across cosmic time. All of it rests on a number set in the first second of cosmic history. You are here because the books did not balance. You are made of survivors. The mechanism that saved them is one of the great unsolved problems in science. And the search to understand it continues, in tunnels under mountains, in detectors under oceans, in the patient work of generations who will not stop until they know why anything exists at all.